Okay, let's start our lesson today. Yesterday we did a bit about polynomial, but more into the focus. The focus was more into synthetic division and how to use them. Now, so if I summarize the polynomial parts that we did yesterday, we have the following. C is a zero of a function px. It means, by definition of zero, it means pc equals 0. By the way, this is true for all functions. It doesn't have to be a polynomial. Okay, it's true for all functions. So when we say c is a zero of a function, means the value of the function at c is 0. Now then, we also learned yesterday that if PC equals to 0, then 0 x minus c is a factor. Of px. That's by factor theorem. Oh, sorry. I think I need to go to the remainder first. So the remainder is equals to 0. Equals to 0. If px divided by x minus c, then the remainder is 0. That's by remainder theorem. And then if the remainder is 0, then x minus c is a factor of px. That is by factor theorem. Okay, and therefore, the consequence is, if c is a 0, it means x minus c is a factor. Now, in addition, if, let me use green, if c is a real number, then x comma c comma 0 is an x-intercept. Is an x-intercept of px. Okay, so why do we want to know that in advance? Because for us to find the x-intercepts, that's the big goal. For us to find the x-intercepts, we need to find the zeros of px. Okay, we need to find the zeros of px, and if that's a complex number, then if it is not a real number, then it's not an x-intercept. But if it is a real number, it is an x-intercept. Okay, now then to find the zeros, what we will do is to find those c's such that pc equals to 0 by using remainder theorem. And once we know the remainder is 0, then x minus c is a factor. Now, the consequence is, if x minus c is a factor, we can divide px over x minus c, and the quotient is a factor, is also a factor. So we can factor further. Okay, that's the plan. Now, what we are going to do today are to use all the possible theorems, foundations that we can get to predict and to guess, educated guess, those C's. Now, it's not like factoring thingy that you can do factoring and get the zeros, right? if that's degree of 2. Once it is degree of 3 and on, then more or less we need to do some guessing. Now, this theorem helps us to provide some educated guessing, okay, and of course speed us up. Okay, now let me start. First one about a polynomial. Polynomial. A polynomial looks like a polynomial, or to be more precise, a polynomial function of degree n, denoted by px, but our textbook denotes that by a regular function fx, looks like px equals to a sub n x to the n plus a sub n minus 1 x to the n minus 1, a sub n minus 2 x to the n minus 2, all the way to down to a sub 2 x squared, a sub 1 x to the 1, and a sub 0. Okay, now I know it sounds, it seems to be very complicated, but it's basically trying to say that the exponent is in descending order. Okay, and we start from the highest exponent. Okay, and the highest exponent of that polynomial represent the degree of that polynomial. Okay, so the degree, when we say the polynomial is degree n, it means that the polynomial, the term in px in the polynomial have degree at most n. Okay, the highest, to be more precise, the highest degree of the terms in px is n. That's actually a more precise way. Okay, and the a sub n minus 1, a sub n minus 2, so on and so forth, represent the coefficients of the term of the for that degree. So, for example, if I have, let px equals to negative 7x to the 5th plus 2x to the 4th plus, let's say, 3x squared minus 6x plus 9. Let's say we have something like this. Then this polynomial, it has the degree, usually denoted by n, the degree n equals to 5. That's the highest exponent. Okay, that's the highest exponent. Now, the leading coefficient, a sub n, is called the leading coefficient. That's the coefficient for the term with highest exponent. Okay, leading coefficient in this case, a sub 5, that's negative 7. Okay, so when you see a sub 5, that's the coefficient of the term with exponent 5. Okay, that's leading coefficient. Leading term is the term with the highest exponent. Leading term will be the term with highest exponent. So in this case, the leading term is negative 7x to the 5th. Okay, that's the leading term. Now, then the constant term is a sub 0. The one without any x. the one without any x. So in this case, the constant term is 9, which if you think about it, actually we get one thing right away for the graph later on. That will also give us the y-intercept. Y-intercept of a polynomial with constant term a sub 0 is 0, a sub 0. Okay, now in this case, the y-intercept is, maybe I use blue instead. The y-intercept for this graph, if we graph that later on, the y-intercept is 0, 9. Okay, and actually, if you think about it, we already seen this in linear function. A small example here, if I have fx equals to 2x minus 1, notice that linear function is actually a polynomial. Okay, it's two terms. Now, then from here, you see that the y-intercept, as we have learned before, is 0, -1, right? Just a little example. So the fact that the y-intercept is 0, the constant term is a fact that we have used even from last week. Okay, so that's nothing really new there. Now, that's for the polynomial and its component. Now, I need you to start getting used to the notation because we use this a lot, especially for this chapter. Okay, we use this a lot. The one that's important are especially this guy here, the leading term, and the constant term. Okay, those are the one we really need you to realize and kind of like in your subconscious what they are. Now that's for polynomial and its component. Now, far ends behavior. Far end behaviors is basically to tell us, informs us where the graph of the function of a function going to when x goes to infinity and when x goes to negative infinity. And this actually, this is the intuitive definition for every function, not only for polynomial. Okay, so when we say far ends behavior means what happened, basically want to answer this question. As x goes to positive infinity and fx goes to what? As x goes to negative infinity, then fx goes to what? Okay, now it turns out that when it comes to polynomial, when the function is a polynomial, then the function, the far end behavior is determined by its leading term. Now the logic is because the idea is because the logic. When x is very positive, very large positive numbers, very large positive number, then the leading term, the value of the leading term becomes very dominant. Okay. Some little example here, just to explain that. Suppose I have this. For example, I have px equals to 3x squared minus 100x plus minus 700. Okay. Now, yes, the leading term has coefficient only 3, right? Okay. But the thing is, when your x is very large, imagine when x is very large, let's say I use, for instance, for example, I use x equals to 10,000. Now, of course, x supposed to be even larger than that, right? Okay, even larger than that, because we go very, very far to the right. Now, when x equals to 10,000, notice that the value from this yellow shaded part is a lot more significant. It becomes a lot more significant. 3 times 10,000 squared, right? Minus 100 times 10,000 minus 700. Let's use minus here. Okay, now you see that this may be millions. This may be million, or is it billion? 10,000. Yeah, this may be millions. But this part here already billions, or even more. Okay, such that if you already have $100 of billions, hundreds of billions, and then somebody say, give me 1 million, you may just slap that person with that $1 million, and you even smile. Okay, so what I'm saying is that what I'm saying is when x becomes very large number, the contribution of the value from the remaining terms is not significant anymore. Okay, such that the value of this P 10,000, P 100,000, or P 1 million is basically decided by the leading term. Okay, basically decided by the leading term, and that's when that's why I say that it's determined by the leading term, because that's the dominant one. Okay, that's the dominant one. Okay, so and you can see likewise when x is very large negative numbers. When x is very large negative numbers, so it's negative numbers, but the magnitude is very large, like negative 10,000, negative 1 million. The same phenomena happen. Then x, the value of the leading term, and the value of the leading term becomes very dominant. A lot more dominant compared to the rest of the terms combined. Okay, so in other words, in practice, then, if you give me a polynomial, this 3x squared minus 100x minus 700, and I want to know how will this polynomial behave in the when we go very far to the right, very far to the left, we just look at the far end behavior depends on only the leading term, 3x squared. What do you know about 3x squared? And if you think about this, when we learn quadratic function, this is quadratic function, right? Because the leading, it's quadratic, then we see it's quadratic, it's degree of 2. Okay, it's quadratic, so we know it will be parabola. It's either opens up or opens down. And then we see, oh, it's 3. So it must be this one opens up and not opens down, right? Then from there we see if we go very far to the right, then the parabola will go up to infinity. And when we go very far to the left, it will go up to infinity also. Okay. In other words, borrowing these examples here, then as x goes to infinity, that polynomial, the value of that polynomial will also go to infinity. As x goes to negative infinity, the polynomial also goes to negative infinity. I'm sorry, positive infinity. Okay, now I usually say informally in my test that it will be top. Means if you go very far to the left, when x goes to negative infinity, then the function, the graph of the function will be on the top left. When you go very far to the right, then the graph of the function will go to the top right. Okay, that's my informal notation, but this is actually the more precise notation. This is actually the more precise one. But I'm okay if you just answer it this way. Okay, I'm okay if you answer it this way. This is the correct notation, the proper notation. Yeah, you will start using this proper notation in calculus. For now, you can just use top, or later on you will see bottom, bottom, top, bottom. Okay, and so coming back here, I use that little section on the right-hand side to explain you the logic and what we actually do. Okay, now then, because of that logic that the far end behavior is determined by leading term, then we can summarize it right away with the following. It depends on the leading term, an x to the n, right? The leading term. Now, then when the n is an even positive integer, when n is even, then it's either going facing up or facing down. Okay, just like your x squared, okay, the one in our example, but this also applies for x to the 4th, x to the 6th in the leading term. Now, it opens up if the leading coefficient is positive, opens down if the leading coefficient is negative. Okay, now the thing is, we don't know what happened in between though. We don't know what happened in between. Oops. Yeah, we don't know what happened in between. Okay, so it's actually up and down, the in-betweens, we don't know. But when we go very, very far to the right, for this example, okay, when we go very far to the right, it will be going to positive infinity. Very far to the left, it's also going to positive infinity. Okay, now when the leading coefficient is negative, for quick example, let's say we have fx equals to negative 1/2 x squared plus 7x minus plus 10. You know, yeah, the coefficient, the exponent is even, the degree is even, so it's either one of these two. And because the leading coefficient is negative, then we know it's actually upside down parabola. Okay, now we will have the same far end behavior even if I change that 2 becomes 4. Even if I change that 4 into 14, it will still have the same far end behavior. Of course, how the graph behaves in between, we don't know. It will change, right? But at the very end, We know it will go to negative infinity, and both ways, you go to the right or to the left. Now that's for a very, very fast example. Now, what happens if the degree is odd? If the degree is odd and the leading coefficient is positive, then it will look like this. Okay, again, we don't know what happened in between. Now, if the leading coefficient is negative, you basically flip that upside down, so it looks like this. Again, we don't know what happened in between. Now, I usually say, for this case here, this is top, top. This is bottom, bottom. Or you can also call it down, down. Okay, this is bottom, top. From the bottom left to top right. Okay, and this is top, bottom. Okay, so for a quick example, let me use the polynomial we have above here. And use the polynomial that we have above there. This time a little smaller. Okay, then the far end's behavior will be, notice that the degree is 5, which is odd, and the leading coefficient is negative. Okay, so when we go very, very far to the right, when x is very positive, x to the 5th is positive times -7, it becomes negative infinity, right? Okay, so on the far right, it will be at the bottom. When we go very far to the left, when x is negative infinity, then x to the 5th will be negative infinity. Multiplied by a negative number becomes positive infinity. So it becomes top. Or to be more precise, as x goes to positive infinity, the px will go to the bottom, which is negative infinity. And as x goes to negative infinity, the value of the polynomial will explode to positive infinity. Okay, now once you shape your intuition that way, eventually you will achieve or memorize this table. Okay, yeah, once you do enough problems, then you will see you come up with that table. You can try to match with what we learned yesterday. And see that the graph that we have yesterday. Let me take a look. Let me show you what we had yesterday. This one here. You see, this is degree of 4 with leading coefficient positive. Now, according to our theory just now, we find that this is a on the top left, on the left-hand side, it will be infinity. On the right-hand side, it will also be positive infinity. Right, and look at the graph. You see, when you go very far to the right, the value actually explodes to infinity. Right, when you go very far to the left, the value of the function also explodes to infinity. Okay, that's what we learned yesterday. Let me clean this up. Come back here. That's for the far end's behavior. Next, how do you use this? This actually helps us later on, especially when we do the graphing. Okay, so that's a little aspect of the graph that we need to pay attention later on, but it's way too easy. It's way too easy. Next, fundamental theorem of algebra. Fundamental theorem of algebra. Fundamental theorem of algebra. It says that the thing is, I will not use the correct version of fundamental theorem of algebra. The following is the precise fundamental what fundamental theorem of algebra says. It says the following: if polynomial px, if px has degree of n, then I think I should say with complex coefficients, including real numbers, okay? Including real numbers, complex coefficients. Remember the coefficients of the polynomials we talked about? These are the coefficients. Yeah, all of them here happen to be integers, but the coefficients may be fractions, may even be that's rational numbers, can be real numbers like pi maybe, okay? It can also be a complex number like 2 plus I, okay? 9 minus I, 9 minus 7I, so on and so forth. Okay, so those are what we meant by complex number. Now, with complex coefficients, then Px has at least one complex zero. One complex zero. Now, don't forget, at our level, when we say a zero of a function, it means, let's say the complex zero of that polynomial is c, it means pc equals to 0, okay? It doesn't mean it is x equals to 0, no. X can be 3, but p3 equals to 0, that's why we call that complex zero. Okay, now that's fundamental theorem of algebra, but the consequence of this fundamental theorem of algebra is the one I want to use. Our textbook give it a different name. Different name, but I would just quote it as if it is a fundamental theorem of algebra. Okay, the direct consequence is that the following: if Px has a degree of n, with complex coefficients, so that includes all the polynomial we will be dealing in this course, then Px has n zeros. Up to multiplicity. Multiplicity. I think I should say counting multiplicity. Okay. Now the explanation is because Px now becomes a sub n times x1 minus c1, x2 minus c2, all the way to xn minus cn. Basically, if you have a polynomial, then you can factor it in a way that you find, if you have degree of 5, for example, then you must be able to factor it with the leading coefficient here. This is the factor form. This is the leading coefficient. And it will be x minus something, x minus something, x minus something, x minus something. You can always write it that way. Okay, always, always, always. Now, the core in our course, of course, we will be dealing with, even if we have complex zero, a zero which is a complex number, then it will be a simple complex numbers. Okay. Now, the one that we really take from here is if it is degree of n, then it must have n zeros. No more, no more, no more than n. Okay. Now, this fundamental theorem of algebra says it's no more than n, but also no less than n. So if you have degree of 5, you should have 5 zeros. Okay. Now, some of the zeros may be the same. Give you some short illustration. For example, we have learned that if we have fx equals to x squared minus 3x minus 4. Okay. Remember, we can factor this. This is x minus 4, x minus 1. The leading coefficient is x plus 1. The leading coefficient is 1. Right? This is 1 here, so this is 1 here. Okay, so the leading coefficient a sub 2 equals to 1. Okay, the zeros are x equals to 4, x equals to negative 1. Right? So you see this polynomial can be written in factored form, and from that factor forms we get the zeros. And if the zeros are integers, like are real numbers like this, then we have x-intercepts. Remember, in your tests and quiz, I emphasize that when it comes to x-intercept, you need to write it as a coordinate, because you need to distinguish between x-intercepts and zeros. Okay. Fundamental theorem of algebra says that any polynomial with degree of n must have n zeros. But some of them may not be real numbers, such that you may have less number of x-intercepts. Okay. Now, what does it mean, Thomas, when we say counting multiplicity? Another example, suppose I have fx equals to negative 2x plus 3 squared, x minus 1 cubed, x plus 4. Now then, the zeros are x equals to negative 3 with multiplicity of 2. Multiplicity of 2. Multiplicity of 2 because it happens twice there. Okay. Now you will see the contribution of this multiplicity. What this multiplicity will do later on, it helps us in deciding the sign graph. Okay, now let me go on. The zeros are x equals to negative 3 with multiplicity of 2, x equals to 1 with multiplicity of 3, and x equals to negative 4 with multiplicity of 1, which we also call, if it is multiplicity of 1, then we also say x equals to negative 4 is a simple zero. Okay, so the term simple zero, I don't know if they use this notation. I don't know if they use this terminology in our textbook, but simple zero simply means it is multiplicity of 1. Okay, if a zero is a simple zero, means that zero has multiplicity of 1. Okay, so let me put that 3 here, the multiplicity of 3, and the multiplicity of invisible 1 here, right? Okay, invisible 1 there. Okay, so coming back here, fundamental theorem of algebra tells us how many zeros it has, a polynomial has. It also means how many zeros we need to look for. Okay, how many zeros we need to look for. So like this guy here in our last example, this is a polynomial with degree of what? What is the degree? The degree of 2 plus 3 plus 1. That's the degree of 6. That's the degree of 6. Okay, which means if you have polynomial degree of 6, you need to look for all 6 zeros. Okay, when you solve an equation with degree of 6 later on, then you should have 6 solutions. Some of them may be the same. Okay, some of them may be the same. That's where the multiplicity happens. Okay, so when I say some of them may be the same roots, the same zeros, the same solutions, that's because it happens more than once on that same number. Okay, that's fundamental theorem of algebra. We call that fundamental theorem of algebra because that tells us how many targets we need to shoot. Okay, how many zeros we need to achieve. That's for fundamental theorem of algebra. Now, going further, after fundamental theorem of algebra, a short note, or short conclusion, the number of turning points on the graph of Px with degree n is at most n minus 1. Okay, so for little examples, this is way too easy. This is way too easy. For example, if I have Px equals to 3x squared minus 4x plus 6. Now, when you graph it, you know it will go open up, right? Okay, it will open up. Okay, now the turning points is this one. This is the turning point. That's the turning point. In calculus later on, when we say the number of turning points, it's also called critical number. In calculus later on, if you took calculus before, or if you go to calculus later on, then the terminology turning points refers to the critical number, either the local maximum or the local minimum. Okay, now we can also have, let's say, Px equals to the one we have earlier, negative 7x to the 5th, blah, 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 right? That's the degree of 5. Okay, so it will be something like this. It may look like this. In which, well, it's the degree of 5, so it's bottom top or top bottom. Leading coefficient is negative, so the far end's behavior will be positive infinity on the left hand side, negative infinity on the right hand side. Okay, now it may have 5 zeros, 1, 2, 3, 4, 5, maybe. Okay, okay, but the number of turning points here refers to this. It returns 1, 2, 3, 4. Now, don't forget that the word I use, the phrase I use here is not that the number of turning points is exactly n minus 1. No. It's not exactly n minus 1, but at most n minus 1. At most n minus 1. Because the graph may look like the following. The graph may look like, I don't know what the graph actually looks like, okay? But the graph may look like this. Okay. In which the number of turning points only 1 and 2. Okay, and some of the zeros happens to be complex number. Okay, so if you see a graph, let's say you see the graph looks like this. So suppose the graph looks like, if you see a graph looks like this. Now, find what is the degree of this, the polynomial with this graph. What is the degree of px with this graph? We know because it's top, and one thing we know, n must be even. Even more, the leading coefficient is positive, right? Because it's top. Okay, now let's count how many turning points. 1, 2, 3, right? Okay, 3 turning points. That implies the degree n is at least 4. At least 4, because the degree of 6, okay, 6 minus 1 is 5, okay? At most 5, so the number of turning points 3 may have degree 6, right? At least 4, the degree of this polynomial at least 4 because it has 3 turning points. There could be some bending here that we don't see, that we don't count as turning points, okay? Yeah, but if it has 3 turning points, then the degree of the polynomial is at least 4. Now we know it will be either 4 or 6 or 8 because of that fit behavior. Okay. Now that's for the number of turning points. Now, then the next thing I will do is something quite important, and we will practice more on this later on, something called the Descartes rule of sign. The Descartes rule of sign. As I know, the Descartes rule of sign is, it bears the number of Descartes. It's because the one who invented that is René Descartes. I think I should say René Descartes. Descartes. Is the S part of his name or not? Oh yeah, it is. It is part of his name. So the Descartes rule of sign. Yeah, I wrote it incorrectly earlier. I wrote it incorrectly here. Yeah. It's the same person who invented Cartesian coordinate system. Okay, so you know that this theorem, these rules here is actually very, very old already, as old as, pretty much as old as almost as our rectangular coordinate system. Okay, now, but it's now 12 o'clock, 11:59. Let's give ourselves some break. We come back at 12:10. Then I continue on this later on. So let's start again. Before I get into the Descartes rule of sign, let me first define what we mean by variation of signs. variation of sign. Okay, I start with this. Let Px be a polynomial in descending order. Okay, emphasize in descending order. Actually, that's a given. Once I say a polynomial, then you should actually see that in descending order. But to emphasize that, I write it there that it is in descending order. Then the number of variation of signs, then the number of variations of signs is the number of times the two consecutive coefficients have opposite signs. Or how many times the coefficients actually change signs. Okay, so let's say, for example, if I have Px equals to 4x cubed minus 5x squared plus 7x plus 2. Now then the number of times the sign change from positive 4 becomes negative 5, we change one time, right? From negative 5 to positive 7, we change another one time. Now from positive 7 to positive 2, it doesn't change. So there are two variation of signs. Two variations of signs. Okay. And again, it has to be in descending order. Okay, it has to be in descending order. Now, what happens if we jump terms? Let's say if I have negative 9x to the 5th, and then plus 4x cubed, and then plus 7x minus 3. Let's say we have something like this. And notice that we jump from to the 5th and cube. So we're missing the degree of 4, right? Now, the thing is, we don't worry about it. We don't worry about it. We still count it as long as it is descending in descending order, and the number of times the sign change will count as 1. Okay, now there's no sign change here. There's one more time sign change here. So there are two variations of signs. Okay, that's what it means by variation of signs. Now, then, what Descartes say is the following. What Descartes say is the following. What the Descartes rule of signs says the following. There are two parts. The first part, there are two parts, but I will do the first part first, okay? The first part. The number of positive zeros of Px is equal to the number of variation of signs of px in px or less than that number by an even number. An even integer to be more precise. Okay, let's do a little example to explain what it says. Suppose my px is x squared minus 3x minus 4. Now, how many times the sign changes here? Degree of 2, it changed one time. It doesn't change here, right? So it changed one time. So px has one positive 0. Okay, yeah, that's what this Descartes law sign says. Now, some little note, and I would like to explain it here now. If fundamental theorem of algebra tells us the number of zeros px has, including complex number, then Descartes' rule of sign tells us further how many positive, and later on the second part will tell us how many negative, and therefore non-real. Non-real 0. Okay. Now, once you have a positive 0, then it must be a real number, right? That also implies, so implicitly, this Descartes' theorem, the first part of Descartes' theorem, Descartes' law of sign also tell us that it has one X-intercept to the right of y-axis, on the positive side of on the x-axis. Okay, that's what Descartes' law of sign says. Now I purposely choose this example because we can factor it, okay, and then confirm this is x minus 4, x plus 1, right? Okay, so the zeros are 4 and negative 1. So the x-intercepts are 4, 0, negative 1, 0. You should know how to do that already, okay? We have this question in your test 1. Now, And when we try to sketch this graph here, we know that the x-intercepts are 4, 0, negative 1, 0, and I think the y-intercept is negative 4. So it looks like this. Okay, now the one positive 0 that we said earlier refers to this guy here. That's the one positive 0. Okay, that's the one positive 0. Now, the thing is, it also has this saying that either it is equal to the number of variations, or that number subtracted by an even number. So let's say you get 4 variations. So another example, suppose Px has 4 variations of signs. Then according to the Descartes rule of sign, then Px has either 4, or subtract by 2 is 2, or subtract by 2 is 0, positive zeros. Okay. Now this helps us as the following. Now suppose our main goal of this today's lecture, the main goal is to find out all the zeros such that we can find the x-intercepts, therefore we can graph them, graph the functions, right? Okay, but when we try to find those x-intercepts, we need to find the zeros first, okay? For us to find the zeros, we need to know how many is supposed to be there. From fundamental theorem of algebra, we know there should be the number of zeros equals to the n, equals to the degree. Okay, equals to the degree. Now, the thing is then, the Descartes rule of sign helps us to actually dissect that even further. Now, of those degree of n, how many of them on the positive side? How many of them on the negative side? Okay, so suppose if I have a polynomial with 4 variation of signs, and we found 3 positive zeros, then you need to look for the other one. You cannot stop at 3. You need to look for the other one. If you have only 2 so far, then you may be able to stop. In other words, if you don't find anything anymore, you are fine, because with 4 variation of signs on Px, then it may have only 4 or 2 or 0 positive zeros, or no positive zeros. Okay, but you cannot have 3. If you have 3, you need to look for the other one. If you have only 1, then you need to look the other 1 at least. It may be the other 3. Okay, but you cannot stop at 1 positive zeros. You cannot stop at 3 positive zeros. That's what the Descartes rule of sign says. Now, the second part of this Descartes rule of sign is this. The number, you know what, I'm lazy. Let me copy paste. In fact, doing copy paste may enable you to see the change between the first part and the second part of this rule. Okay, the second part is the following. The number of negative zeros, so I change this to negative, okay, the number of negative zeros of Px is equal to the number of variation of signs of P negative x, or less than that number by an even integer. Okay, now let's see. Suppose I go here, I use this example again, see, lazy guy, right? Suppose I have this polynomial. Copy that. Put it right here. Now, let's say that's the polynomial. Okay, and I want to find the number of negative zeros. Then I see first what is p negative x. P negative x is negative x squared minus 3 times negative x minus 4. That's equals to x squared plus 3x minus 4. Okay. Now you will see, if you do this enough number of times, you will see if the degree is even, replacing that x by negative x will not change the sign. But if the degree is odd, replacing x by negative x will change the sign. Okay. Yeah. I hope that actually make your work faster by observing that. But you need to do some first to realize what actually happened in between. Okay. Now then, see how many times the sign change. There's no variation here. Positive becomes positive. There's no variation. From positive becomes negative. That's one time. So you have one variation of signs. Okay. Now with one variation of signs, when you subtract by 2, it becomes negative. That's impossible. So you must have one negative 0. And that negative 0, that one negative 0 refers to this guy. Okay, so you see from fundamental theorem of algebra says the number of zeros is 2, which is equal to the degree, right? Okay, now then the scatter signs actually break it up even further. One of them positive, the other one negative. Now, how about the other examples? Do I have other examples? Let me use this example here. Let me use this example here. This guy. Let's use that guy. For example, 7x to the 5th plus 4. Actually, nothing is happening to it now. Doesn't matter actually. And then minus 3. Okay, so we have computed the number of signs change here. So 1, nothing, another 1. So they are 2, right? So the number of positive zeros, 2 or nothing. It's either 2 or no positive zeros. Now, how about negative zeros? Then we see p negative x will be 9x to the 5th minus 4x cubed minus 7x minus 3. Okay, how many times the sign changes? It's one time here, no time here, no time here. Okay, so the number of negative zeros for sure is only 1. Okay, now, so if we observe that the fundamental theorem of algebra says it should have 5 zeros, okay, it should have 5 zeros, and the number of positive zeros, it's either 2 or 0. The number of negative zeros is it's 1. So 2, 1 or 0, 1. So how about non-real zeros? The total has to be 5, right? So either you have 2 non-real zeros or you have 4 non-real zeros. Okay, Non-real refers to a complex which is not a real number. So we know we need to look for 5 zeros, okay? At most 2 of them positive, only 1 of them negative. Then we know we will have 2 of them complex numbers, the complex which is not a real number. Or you may have no positive zeros. For sure we will have 1 negative zeros. Okay? And therefore, if that's the case, then we will have 4 complex zeros. Now that's for this Descartes row sign. Now we will get into this again once we get to 3.3. I will explain all the theorems first, okay, and then we do more practice later on. Next one, the one that is easy, okay, intermediate value theorem. Let me do it here. Intermediate value theorem. Intermediate value theorem is a theorem that applies to all continuous functions, not only polynomial. Applies to all continuous functions. Okay, now polynomial happens to be one of those continuous functions. Okay, so my intermediate value theorem here will be out on a polynomial function. Okay, now what it says is the following. Let Px be a polynomial and PA, PB have different signs. Then, actually, this is not precisely what polynomial intermediate value theorem says. Let me erase this. Maybe I say it this way. And let's assume A is less than B. Okay. And on the number line, A is to the left of B. Then Px for any y between PA and PB, then for any y between P and PB, there is at least x equals to c such that TC equals to y. Now, here's the situation. Suppose I have continuous functions like this, like that. Okay, and let's say this is A, and therefore this is PA, right? And this is B, therefore this is PB. Now, what it says is the following. if you pick any number between A and B, any y, let's say I pick this number y here, okay, then there must be at least one x, there's one value c such that the value of that polynomial at c is equal to y. There's a c in this interval AB. Okay, so I'll give you a small illustration. I give you a small illustration in our daily life for this. For example, at 7 a.m. this morning, the temperature is let's say the temperature was 20 degrees Fahrenheit. Now at noon, the temperature is, oh no, 20 is way too cold. Way too cold. Make it 60 degrees Fahrenheit. I have Celsius in mind. Temperature is now 90 degrees Fahrenheit. Okay, then there must be sometime between 7 a.m. to 12 noon when the temperature is any number between 60 to 90, is let's say 80 degrees Fahrenheit. Okay, at 7 o'clock in the morning, it's 60 degrees Fahrenheit. At 12 at noon, it's 90 degrees Fahrenheit. So even if the temperature goes up and down, okay, then any number you choose between 90 and 60 degrees Fahrenheit to 90 degrees Fahrenheit, you choose any numbers in between them. Let's say I choose 80 degrees, okay? Then there must be some time in between 7 o'clock and 12 o'clock where the temperature is 80 degrees Fahrenheit. Okay, because temperature, as we know, is supposed to be a continuous function. Now, the temperature may change dramatically, but still it doesn't change from, let's say, 60 degrees Fahrenheit, and then all of the sudden, in no time, jump to 90 degrees Fahrenheit. No, it won't happen. It won't happen. Okay, it won't happen. Okay, temperature, as we observe right now, at least through human history, is continuous. Okay, it's continuous. So if in the morning it's if in the morning it's 60 degrees Fahrenheit and at noon it's 90 degrees Fahrenheit, then somewhere in between it hits 85 degrees Fahrenheit. Sometimes in between it hits 70 degrees Fahrenheit. Okay. It may be sometime in between less than 60 or more than 90, maybe, but no guarantee, because the curve may look like this. The curve may look like this. The curve may look like this. Okay, yeah. But no guarantee. All we know is everything between PA to PB. Okay, any value you choose in between here, okay, must come from some x between A and B. Okay, that's the guarantee. That's what this intermediate value theorem says. Now, the big consequence of this intermediate value theorem, and that's what I call intermediate value theorem for us here, is consequently if PA and PB, the value of PA is and PB are opposite signs, one of them positive, one of them negative, then there must be a zero in the interval a to b. Okay, to be more precise, it's supposed to be parentheses instead of bracket, but I still can use bracket. Now try to see the following. Okay, suppose I have a coordinate system, and let's say PA is here. Let's say PA is here. This is A. This PA happens to be negative in this case. And PB is here, which is positive. Okay, so you see that the x-intercept, the x-axis is in between. Okay, then however you move, as long as it is a continuous function, however you move from this point to that point, you must eventually hit the x-axis at least once. However you draw it, as long as it is continuous. However you draw it, you must hit that x-axis at least once. Maybe like this, you never know. Right? Okay. That means as long as they have opposite signs, as long as PA and PB has opposite sign, there must be a zero between that A and B. To say even further, then there must be an x-intercept in this case. Okay. Now, how do we use this fact though? How do we use this fact? Let's say, for example, I pick question from our textbook. For example, number 6. So this is 3.1, number 6. I will start doing on problems in the book. 3.1, number 6, we have fx equals to 2x cubed plus 6x squared minus 3. Okay, and the question is, does fx have a zero between -3 and -2? So what you do is you check what is f -3. Okay, you check what is f -3. You can do it this way. You can also use syntactic division if you like, right? So this is 2 times -27 plus 6 times 9 minus 3. This is -54 plus, 54 also, minus 3, that's negative number. And then f -2, I plug in -2 in the x and compute the value. This is still negative. How many go wrong? Plus, I computed it incorrectly. Sorry. It's 6 times -2 squared. So I should have squared here. So this is plus 6 times 4. This is -16 plus 24 minus 3, that's 5. So one of them negative, one of them positive, right? So by intermediate value theorem, there is a zero, maybe more, between x equals to -3 and x equals -2. Okay. Pictorially, if I try to explain this further, pictorially, when x equals to -3, that's -3. When x equals to -2, that's +5. Okay, so from this point going to that point, you eventually have to cross the x-intercept. Okay, you have to cross x-intercept at least once. Okay, now the thing is, Thomas, what then happened? What do we say if they have the same sign, both of them positive? This one here is one of them negative, one of them positive. Like one of them negative, one of them positive. So if they have opposite sign, then it's guaranteed that you have at least a zero in between. What if they don't have opposite sign? Then there's no guarantee. Okay, I think I need to write that as a warning. I need to write that as a warning, warning. The converse is not true. The converse is not true. Okay, in other words, will I say the converse? Maybe let me not using the word converse then. If PA and PB have the same sign, not opposite sign, have the same sign, then intermediate value theorem is silent. In other words, intermediate value theorem doesn't say anything if they have different sign. Okay, because it is possible that they have the same sign, like both of them positive. Okay, and it doesn't have any zero, it doesn't cross x-axis, but it is possible that it does cross. Okay, it's possible that it crossed the x-axis. Okay, so nothing can be said if they have the same sign. If both of them positive or both of them negative, then it may still have zeros in between. It is possible that it doesn't have zeros in between. Okay, so nothing can be said. Only if they have opposite sign, then we have that guarantee. Okay, now let's do number 10. Number 10, same question. 10, let fx equals to x to the 5th minus 3x to the 4th minus 9x minus 6. Okay, and the question is, does fx have any zero between x equals to 3 and x equals to 4, between these two numbers? Again, you can plug that in, but instead of plugging it in, I will use remainder theorem. Okay, so I will use remainder theorem. So 1, -3 for degree of 4, 0 for degree of 3, 0 for degree of 2, -9 for degree of 1, -6 for degree of 0. And then I plug in 3 here. So 1, 0, 0, 0, 0, 0. 0, negative 9, negative 27, negative 33. It's faster, right? I hope you see that it's faster. Okay, so F3 equals to negative 33. What if I plug 4 into that polynomial? 1, negative 3, 0, 0, negative 9, 6. I plug in 4 here, so it's 1, 4, 1, 4, 4, 16, 16, 64. This is 55 times 4, 220. Minus 6 is 214. So F4 is a positive 214 because they have opposite sign. Opposite signs. Then by intermediate value theorem, there is a 0 between x equals to 3 and x equals to 4. Okay. Now, so to be more precise, maybe I say that there is an X-intercept in the interval 3, 4. Okay, there's an X-intercept in interval 3, 4. Now let's go on further. Let's go on further. Number 14. Number 14. The question is, use arrow notation, basically the limit notation, to describe the end behavior of the function. Let's do number 14a and 14b only. That's all we need, actually. So fx equals to maybe 14b, a and c. Fx equals to 3x to the 4th minus 2x squared minus 5. Okay, find the far end behavior. So as x approaches infinity, fx goes to infinity. As x goes to negative infinity, fx still go to positive infinity. Or in other words, in my class, you can just say top. You go to the far right, you go to the top. Go to the far left, it's also go to the top. How about part C? We have fx equal to 2x to the 5th plus 2x squared minus 7x. Then, as x goes to infinity, so you look at this only, the leading coefficient only, leading term only. When x goes to infinity, that will be positive infinity, huh? Fx will be positive, going to positive infinity. And as x goes to negative infinity, fx will approach negative infinity. Okay. You can try plug in negative infinity here. 2 times negative infinity to the 5th, that will be 2 times negative infinity. Right? Negative to the 5th is negative, infinity is still infinity, and this will be negative infinity. Now, this is in proper notation. You are not supposed to write this down. Okay, not even writing it down. No, that's not the right way. Okay, but I hope at this point here, because if we are not being too technical, then this is okay, right? You can see that's what happened. Okay, now then let me go on further. Maybe I do a warning. Don't write this down. Don't write this as part of your formal answer. You can write it on your scratch paper. Okay, you can write it on your scratch paper, but don't write it in your test. Okay, in your test, just give me this right away. Just give me this right away. Okay. Now let me go on further. You see, I start putting things together. I start putting things together. Suppose we do number 26. Number 26 still on 3.1. Number 26, we have let fx equals to x cubed minus x squared minus x plus 1. And what we need to do is actually do the sign graph and therefore sketch the graph. Okay, now I think you can do the factoring for this. Okay, the first two terms is 4 terms, right? The first 2 terms I have common factor x squared. And the last 2 terms I have common factor -1. And then factor further. This is factorization by grouping. And then I go on factorization by difference of squares. So now I get x plus 1, x minus 1 squared. Okay, so to get the sign graph, step 1, critical numbers are x equals to -1 and x equals to 1 with multiplicity of 2. This is with multiplicity of 1. Okay, and then step 2, sign graph. See, remember I teach you the 3 steps to solve nonlinear inequality. Okay, I teach you those 3 steps because the first 2 steps is being used here. The first 2 steps is being used here. Okay, so and then we have -1 as a 0, 1 also a 0. Okay, now the y-intercept, as you can see, the y-intercept of this polynomial is +1. So right away, I can use that to say that the sign here is positive. And because this is multiplicity of 2, which is even, then there will be no sign change. You can try pick x equals to 2, for example. When you pick x equals to 2, what happens? You will see it's positive. And then the guy here, because this is odd multiplicity, then the sign changes. Now, then, how do we use this to graph? How do we use this to graph the polynomial? Now, the x-intercepts are 1, 0, and -1, 0. Okay. Now, we know that because this is degree of 3. Oh, what is the y-intercept? The y-intercept is 0, 1. Now, we know because this is degree of 3 with leading coefficient positive, then the graph must be going to -infinity on the left-hand side, and on the right-hand side will go to +infinity. Okay. The far end's behavior is bottom top. Okay. Now from the sign graph, then I see that to the left of -1, to the left of -1, it is below x-axis. Between -1 and 1, it is above x-axis. Okay. and between 1 to infinity, it's still above x-axis. Still possible. Okay. Now, so we see from here further conclusion that if the multiplicity is even, then the graph will bounce on that x-intercept, at that x-intercept. Okay, and in fact we can say more. It will bounce according to the degree. So we can say that the way the graph actually behave, in surrounding of this one here, it behaves like a square because of the degree of 2, x squared, right? It behaves like a square. While at -1 here, it behaves linearly because it's the degree of 1. So later on, if you have a 0 with degree of 3, then it will behave like an x cubed. Okay, when you cross x-axis there. Okay, so if you see, for example, if you see this graph, let me sketch another one. Yeah. Suppose I have the graph that looks like this. Suppose I have a graph looks like this. Okay. Suppose I have a graph look like this. Now this is not degree of 1 for sure. Okay, this is not degree of 1, not degree of 2. Thomas, you have 2 turning points. So the degree must be 3. Actually, even more, because this is degree, even degree here, right? Now, but this one will not be degree of 1. That kind of 0, the way it behaves around that x-intercept, it doesn't cross that as a line, it crosses that curvy, right? So this must be multiplicity of an odd multiplicity. It's an odd multiplicity, and it must be at least 3. It's either degree of 3 or degree of 5. Now this one here is even, okay, because it behaves like that, then the multiplicity at least 2. So this polynomial must be a polynomial with multiplicity at least 5. It must be odd. In total, the multiplicity must be odd. I mean, the degree must be odd. Okay, in total must be odd, at least 5, either 5 or 7. It won't be degree of 3. It won't be degree of 3. Okay, so that's even more details, which I don't think our textbook actually provided to us. Yeah, I don't think that our textbook actually provided that illustration to us. Now, the thing is, on this section, in this section, we actually see a polynomial that is factorable. In this section, we see the polynomial to be factorable. Okay, in 3.3, we will learn even more. In 3.3, we will learn in rational zero theorem. Okay, that's one of the key theorem that we need. And then after the rational zero theorem, what else? That's the key though. Without rational zero theorem, we cannot do that much. And conjugate zero theorem, which is not really a big deal. We actually already learned that implicitly. Okay, but let's take a break first. Let's take a break. Right now it's 1:05. Right now it's 1:05. We come back at 1:15. Okay, let me continue. This time I will still work on problems from our textbook, from section 3.3. 3.3. Let's do, for example, number 2, the easy one. It's number 2, so how hard can that be? Number 2, it says the following. Find a polynomial of degree 3, find a px of degree 3 with zeros. The zeros are -5, 2, and 4, and P3 equals to -24. Solution, because the zeros are x equals to -5, x equals to 2, and x equals to 4. There are 3 zeros here. There are 3 zeros here, and it's the degree of 3. So each one of them must be a simple zero. It must be a multiplicity of 1. Then by factor theorem, okay, x plus 5, x minus 2, x minus 4 are factors of px. Okay, in other words, px equals to some coefficient times x plus 5, x minus 2, x minus 4. Now notice that I now write the polynomial in factored form. Okay? Okay. Now the thing is, I still need to find this thing. I need to find that thing. It's already degree of 3, but I still need to find the leading coefficient. Now I will use this guy to help. Okay, I will use that guy to help. So P3 equals to the leading coefficient times 3 plus 5, 3 minus 2, 3 minus 4, and P3 is -24. So -24 equals to the leading coefficient times 8 times 1 times -1. So -24 equals to -8a sub n, then the leading coefficient is 3. So Px is, in factored form, it is 3x plus 5, x minus 2, x minus 4. If I need to make it into descending order, I need to FOIL them, right? So this guy, let me multiply these two first. Multiply these two, then I get x squared plus 3x minus 10 times x minus 4. And then you do the long FOIL if you like. Okay, let me see what will this be. This will be 3 times x cubed. How many x squared? -4, 3, -x squared, how many x? -12 plus minus 10, that's -22, plus 40. So multiply by 3, that will be 3x cubed minus 3x squared minus 66x plus 100. That's the polynomial. That's number 2. How about number 10? Same question. Number 10, it's a similar question. So the n, the degree is 4. The leading coefficient is 1. And the zeros are 5 with a -5 with multiplicity of 2. And 2 with multiplicity of 2. Okay, now then by factor theorem, by solution, by factor theorem, x plus 5 is a factor with multiplicity of 2. X minus 2 is a factor with multiplicity of 2. So the polynomial now, must be the leading quotient times x plus 5 squared, x minus 2 squared. But they say the leading coefficient is 1. So our px is simply x plus 5 squared, x minus 2 squared. Then let's FOIL that. The first one will be x squared plus 10x plus 25. Second one is x squared minus 4x plus 4. If I FOIL that further, you may wonder how I did that fast because of this. Okay, the highest degree will be degree of 4 because x squared times x squared, that must be x to the 4th, right? And that's the only way to get x to the 4th. Now, how to get x cubed? To get x cubed, I need to pair this guy with this guy. And this guy with this guy. Oh, I have double x squared. Okay, so I get negative 4x cubed plus 10x cubed. That will be plus 6x cubed. Plus 6x cubed. Now, how about x squared? X squared will be this pair. This gives me x squared. This also gives me x squared. This also gives me x squared. So the one on the left-hand side goes to the right. The one on the left-hand side goes to the left. Okay, so the first pair gives me 4x squared. The second pair minus 40x squared. And the last pair gives me plus 25x squared. That's negative 11x squared. Negative 11x squared. Then how about to get an x? The coefficient of terms with x, that's negative, I'm sorry, positive 40 minus 100. That's negative 60. X. And finally, the last one plus 100. Okay, that's for number 10. Number 14, this time you need to see the graph from your book. They give us the graph. See the graph from the book. Okay, basically we see the following, that it contains negative 1, 4. Okay, and the x-intercepts are 0, 0, 1, 0, 3, 0, and 1, 2, 3, I'm sorry, 1, 2, 3, or 5, 0. And from the way it crosses, the way each one of them crosses x-axis, we know each one of them has multiplicity of 1. Okay, they tell us though that it is degree of 4, and they give us 4 zeros. Don't you think they're really nice? So the only way that can happen is if each zeros is degree of 1, right? Multiplicity of 1. Okay, so from here we see that the zeros are 0, 1, 3, 5. So the factors are x, x minus 1, x minus 3, x minus 5. Those are the factors. Now then the polynomial written in factored form will be the leading coefficient times x, x minus 1, x minus 3, x minus 5. Now it is said that -1, 4 is one of the point on the graph. So when x is -1, if x is -1, p -1 is 4. 4 equals to leading coefficient times -1 times -2 times -4 times -6. It's 4 equals to the leading coefficient times positive 48, such that the leading coefficient is 4 over 48, which is 1 over 12. So now my polynomial is 1 over 12 times x, x minus 1, x minus 3, x minus 5. Let me FOIL this. Okay, I will do this last. And I FOIL further. This is x cubed minus 9x squared plus 23x minus 15. So this is 1 over 12x to the 4th minus 3 over 4x cubed plus 23 over 12 x squared minus 5 over 4. Okay. That's for number 14. How about number 24? How about number 24? We have a function and they want us to find the zeros and state the multiplicity for its zeros. Find the zeros of fx equal to 6x squared plus 7x minus 5 to the 4th, and then 4x squared minus 1 squared. Seems like we need to factor each one of them. That's why you need to be very good with factoring. This one is 2x plus 1, 2x minus 1, that's a square. This guy here, I believe that's 3x and then 2x plus 5 minus 1. So this will be 3x plus 5 to the 4th, 2x minus 1 to the 4th, 2x plus 1 squared, 2x minus 1 squared. Oh, then my 2x minus 1 now becomes to the power of 6. So the zeros are x equals to -5/3 with multiplicity of 4, x equals to 1/2 with multiplicity of 6, x equals to -1/2 with multiplicity of 2. Okay, so the 4 comes from here, okay, the 6 comes from here, and the 2 comes from here. Number 30. So I do a lot of problems, huh? Number 30. Show that the number is a 0 and express fx as product of linear factors. So we have number 30 fx equals to x to the 4th minus 11x cubed plus 36x squared minus 16x minus 64. Now, the big story that we need to do later on is to find the x-intercepts, the y-intercepts, far end behaviors, how many zeros this function is supposed to have. We know it's supposed to be 4 zeros. How many positive zeros, how many negative zeros, how many complex zeros. Okay, basically in the end, we need to graph it. Okay, now they give us a big help. The big help they give us is they tell us that x equals to 4 is a 0 with multiplicity of 3. Now that's a very big help, because otherwise we don't know any way right now to factor this yet, not now. Okay, so how do we use the fact that x equals to 4 is a 0 with multiplicity of 3 to find the other 0, because they are supposed to be 4 zeros, right? They gave us 1 0 with multiplicity of 3. So we still need to find the other 1 0. Then how do we do that? Knowing some zeros enable us to reduce the polynomial, the degree of the polynomial, down. So in this situation, for example, we know 4 is a 0 with multiplicity of 3. So I can reduce that polynomial using 4 3 times. Okay, you will see that we just need to reduce that to the degree of 2, and then from there we factor it. Okay, but then let's see. Using syntactic division, 1, -11, 36, -16, -64. It's already in descending order and nothing jumps. So this is 1, 4, -7, -28, 8, 32, 16, 64, 0. Now notice that this becomes the degree of 3. Originally is the degree of 4. Now it becomes the degree of 3. Okay, but 4 is a 0 with multiplicity of 3. So let me continue right away from there. I can do 4 3 times. I can divide by x minus 4 3 times because it's the 0 with the degree of 3. 1, 4, -3, -12, -4, -16, 0. Okay, so at this point, this is the degree of 2, which you can actually do factoring already. Okay, so this is x squared minus 3x minus 4. And because 4 is another 0, so far we have 2, right? Okay, we need one more, right? The degree of 3, multiplicity of 3. So this guy, it will be x minus 4 times something, right? And you will find that's what we have. So writing fx as a linear factors, it will look like x minus 4 to the power of 3, x plus 1. So notice that once you get a 0, not only you get a factor, but you can also use that factor to divide, get the quotient, and you get another quotient, and then you get another quotient. Now you get all the zeros instead of only 3. Okay. Now, if we try to, for example, sketch the graph of these, just out of curiosity, Okay. The x-intercepts are 4,0 with degree of 3 and negative 1,0 degree of 1. The y-intercept is negative 64, 0, negative 64. Okay. The exponent, the degree is 4 with positive leading coefficient. So it must be top. Okay. Now then, you can do the sign graph to help, but you will see that it will go down this way. And because this guy is degree of 3, it won't cross linearly, it will cross kind of like this. Okay, approximately that's what the graph looks like. And let's confirm one more thing. How about the Scatters law of sign? Let's see how many times the sign changes. 1 time, 2 time, 3 time, nothing, right? So it has 3 positive zeros or 1 positive zeros, according to the Scatters law of sign. And yes, we confirm that there are 3 instead of 1 positive zeros. Okay, now what happened if we look at the f negative x? F negative x will be x to the 4 plus 11x cubed plus 36x squared plus 16x minus 64. You see that there is no choice, no variation here, no variation here, no variation here, 1 variation here. And therefore, 1 negative zeros, so therefore 1 negative, 1 x-intercept to the left of y-axis. Okay, so the 3 positive 0 we're talking about is here. And 1 negative 0 we're talking about is here. Okay. Now, let's go on to the next one, 3.4. But I basically put everything in one paper right now. They are related. They are related. The next one is intermediate value theorem. No. Sorry, rational zero theorem. That's one of the most important theorem when we deal with polynomial. Rational zero theorem. And it says the following: let Px be a polynomial with leading term a sub n x to the n and constant term a sub 0. Now it says the following: if C is a rational zero of Px, of that polynomial, we say that a rational zero means C is a fraction, can be written as a fraction. So C can be written as P over Q. Okay. No, I don't want to use that Z. I want to use C. Because it's rational, means you can write it as a fraction. Now, if C is a rational zero of Px, then C must be plus minus a factor of the constant over a factor of the leading coefficient. Okay. Oh, actually, I need to add one more. I forgot to say this. Where the coefficients A sub I are integers. Okay, so all the coefficients are integers. If the polynomial has all the coefficient integers, and C is a zero, which is a fraction or can be written as a fraction, then the zero must be a factor of the constant term divided by a factor of the leading coefficient. Let's try to explain this a little bit. Using something we have done before. So for example, if I have fx equals to x squared minus 3x minus 4. If you factor this, you will see that the zeros are 4 and -1. Okay, now notice that this 4 can be written as 4 over 1, and -1 can be written as -1 over 1. Now, the numerator 4 and 1 are factors of that 4. And the denominator 1 here are factors of the leading coefficient 1. Another one. Let's say fx equals to let's say 3x squared, and then maybe minus, maybe plus 4 here, minus 8x. Okay, then if the zero is rational, if the zero is rational, if the zeros are rational, then it must be plus minus a factor of 4, which is 4 or 2 or 1. Let me write 1 through 4. The factor of 4 is R1 or 2 or 4. And the denominator will be the factors of 3. 1, 3. Okay, so the candidates for the zeros of these polynomials will be plus minus 1, plus minus 2, plus minus 4, plus minus 1/3, plus minus 2/3, plus minus 4/3. Now, if you have a multiple choice question, and they ask you the solution of 3x squared minus 8x plus 4 will be part A, 0, 1, 2. You know it won't be 0. How about part B? 1, 2, 3. You know it won't be 3. Okay. How about 1, 2, 4? Maybe. How about 1/2, 1, 2? No, it won't be 1/2. Right? So using method of elimination, you may be able to find the zeros of this, the root of this equation a lot faster by just staring at that and knowing intermediate value, knowing rational zero theorem. Okay. Honestly, I don't know if this is true. In fact, I know this is not the correct one. I don't know if this is true, but for sure it won't be that one. It won't be this one. It won't be this one. For sure, guaranteed. Okay. And when you do SAT, I think SAT 2 math, if you're still in high school and you are planning to take the subject SAT, and I know that's it's multiple choice. Okay, so one technique of solving problems in SAT is by doing process of elimination. Okay, instead of finding a solution, you find 3 wrong solutions. If you can point out 3 mistakes, then the other one must be the correct one. Okay, well, anyway, that's just a brief look into that. I purposely choose this polynomial to be factorable. Okay, so I want to show you that when I factor this, I will find my 0 will be in that list. So the zeros are 2/3 and 2. Okay, so you see that positive 2 and positive 2/3. And this still actually fit the Descartes rule of sign because you see that degree of 2, but it has 2 positive zeros. 2 positive zeros. Right? We confirm that. And when we look at f negative x, we get 3x squared plus 8x plus 4. There will be no negative 0 because there is no change of sign. Okay, now that's the foundation for this intermediate value theorem. Why I keep on saying intermediate value theorem? Rational zero theorem. That's the basic foundation of this rational zero theorem. Rational zero theorems does not tell us if it is positive, negative. The one that tells us positive, negative will be the Descartes rule of sign. But the Descartes rule of sign does not tell us what are those zeros. They just tell us if it is positive or negative. Rational zero theorem only deal with rational zeros. If that's a complex non-real zeros, then it won't be detected by these rational zero theorems. Rational zero theorem. Okay? Okay, let me go on. It seems like I need you to do a lot of suggested homework later on, such that on Monday we will spend 1 hour just to deal with this polynomial altogether. Okay, deal with this polynomial. Our textbook actually break the discussion of polynomial into 4 sections, 3.1 to 3.4. But at the end, we need to answer questions like number 19 to number 30. Which is basically the accumulation of all those topics put together. Okay, let's do this first. For example, let px equals to x to the 4th minus 9x squared plus 7. Okay, and then what are the possible rational roots or rational zeros of px according to rational zero theorem. The possible roots are c equals to plus minus the factor of 7, 1, 7, and the factor of 1 is 1. So it's either plus minus 1 or plus minus 7. Okay, if it is a rational roots, then it will be plus minus 1 and plus minus 7. Okay, now The thing is, how do we show that it has no, how do we show that Px has no rational root? Well, the way is you get all the possible candidates first, and then you check one by one. So basically, P1, you will see P1 is 1 minus 9 plus 7. But you will see P1 basically replacing x by 1. And you will end up seeing just adding, subtracting the coefficients. Now, P1 is -1. So 1 is not a 0. How about P -1? P -1, you will get also 1 minus 9 plus 7. So -1 is not a 0. How about P7? How about P7? Let me do it this way, use synthetic division. That's 1, 0, -9, 0, 7. And not 0. Okay, so 7 is not a 0. Now you will see P -7 actually give you the same number. So basically looking back, if the question is only rational zeros, then there are only 4 possibilities, either positive or -1, and positive or -7. Now the thing is, when I tried each one of them, none of them work, then we can guarantee there's no rational root. Okay, there's no rational root. In fact, you will see later on all the roots are complex roots. Okay, all the roots are complex roots. Let's say, for example, if we go with the Descartes rule of sign, x to the 4 minus 9x squared plus 7. No, not complex root. I should say real number. There are real numbers, but they are not, is it right? Real numbers, but not real numbers, but not complex, not rational. Okay, now according to Descartes' rule of sign, it must have 1 positive zeros. Oh no, actually 2. There's another 1 here, change of sign. So 2 or nothing positive zeros. Okay, how about P -x? P -x, we will get x to the 4 minus 9x squared plus 7. Wow, they happen to be the same, huh? Exactly the same. Okay, so from here we see that there's one variation sign, another variation sign, so it will be 2 or nothing negative zeros. And extra conclusion, because Px is equals to P -x, then the graph, then Px is an even function. And therefore symmetric with respect to the y-axis. Okay. Now let's try to solve this. Let's try to solve this. I set this equals to 0, right? I set this equals to 0, and all of a sudden, I hope you realize that we are looking at a quadratic-like equation. Let u equals to x squared. So we get 0 equals to u squared minus 9u plus 7. It won't be factorable. Okay, I mean, if you look at the discriminant here, there's negative b minus 4ac. That's 81 minus 28. What's that? 53. That's 53. Okay, so u12 will be negative b plus minus square root of 53 over 2 times 1. So u1 equals to 9 plus square root of 53 over 2. u2 is 9 minus square root of 53 over 2. But u is x squared. U is x squared. So when I apply square root property, I will get plus minus square root of 9 plus square root of 53 over 2. You can rationalize that denominator, right? Then multiply the top and the bottom by 2. Then I get x12 is plus minus 1/2 square root of 18 plus 2 square root of 53. And for the second branch, 9 square root of 53 over 2. Now 9 minus 50, the square root of 53 is positive. Well, because 9 is square root of 81. Right? Okay. So it's positive. Once we know it's positive, then we can apply the square root. Okay, that will be plus minus square root of 9 minus square root of 53 over 2. Rationalize the denominator, multiply the top and the bottom 2. That will give us x3, 4. So there are 4 solutions. As we expect, it's the polynomial degree of 4, right? So we have 4 solutions now. Plus minus square root of 9. I'm sorry, not 9, 18. 18 minus 2 square root of 53. Those are the 4 solutions. But you see, so if I spell it out, x1 is 1/2 square root of 18 plus 2 square root of 53. x2 is negative 1/2 square root of 18 plus 2 square root of 53. x3 is plus 1/2 square root of 18 minus 2 square root of 53, and x4 is negative 1/2 square root of 18 minus 2 square root of 53. Those are the 4 solutions. Okay, now let me give you a suggested homework. Suggested homework 3.4a first. Number 1 to number 15. Oh, there's a last one. In 1 minute, I do it. Conjugate zero theorem. If a plus square root of b is a irrational zero. No, I think I want to say complex. Yeah, complex or an irrational zero of px, then the conjugate a minus square root of t is also a zero. Now this applies to complex number, the conjugate for complex number and the conjugate for irrational number. So suppose, for example, if you see 2 plus I is a zero, then 2 minus I is also a zero. Okay. 3 plus square root of 2 is a zero, implies 3 minus square root of 2 also zero. Okay. Yeah, if one of the multiplicity of 2, then the other one also multiplicity of 2. That's what conjugate zero theorem says. Now that's for 3.4. 3.3 you can do actually most of them. Number 1 to number 39, just do every other odd. You don't need to do all of them. Every other odd. This is the odd ones here. And 3.2, we did them yesterday. Done yesterday. I hope you did your homework. And 3.1, number 5 to number 29. Again, just do the odd ones. Okay. So on Monday, I will continue with 3.4, but my assumption is you study all of this already. Okay, you study all of this already, and we will put all of this together on Monday, and then we go on, finish up chapter 3 at 3.5. I plan to give you a homework, which I will post during this weekend, and it will do on Tuesday. Okay, yeah, it will do on Tuesday. I will write it on the board later on. Okay, that's for today then. Bye-bye.